Thank you. It sounds like it's working. So my name is Christian Hogsberg, and I'll talk about Wayland. And if you'll bear with me, I'll just spend the next slide here introducing myself because okay, I will try. I'm gonna spend just an extra slide here on introducing myself, and the thing is, sometimes I sit there and read the internet, and there are people out there talking about Wayland, comments on websites, and they usually talk about how the Wayland developers don't know X, and what do the X org developers really think about Wayland, and what's going on. And so I wanted to just provide some background for what I've done and where I come from. And I used to work for Red Hat in 2005 up till a couple of years ago, and I worked in the X team at Red Hat, and we did things like ARGLX to let compositors, GL-based compositors, run under X, and we did DRI2 that enabled GL applications to work smoothly under compositors such as Compis and Kwin, Modern, and so on. And so we did a lot of work on X back then, and we pushed X forward with compositing. We fixed a lot of the bugs and problems that prevented us from using X in a composite environment. And so we spent a lot of time pushing X forward and trying to get X more modern and usable for what we wanted to do. So I come from a background as an X developer, and a lot of what we've done with Wayland is sort of the natural extension of that work, where we did as much as we could with X, and then we got to a point where we realized, well, we can only do so much with X, and what we have done on top of X now is essentially a new Windows system, which is why people say X is good enough. That's because we built a different Windows system on top of X. And again, I basically want to make the Linux desktop experience better, and that may involve X, or it may not involve X. And I think we've gotten to a point where we have to move forward and move away from X. And so with that out of the way, let's go and look at what Wayland is. It's just a hard question to answer because there are several things in Wayland, but mainly it is a new display server architecture. It's replaces X. It's a standalone architecture for having a display server with clients that let you run a modern, fully complete desktop, and it scales down to mobile devices and embedded use cases. It integrates some of the functionality we have in separate processes under X today. With X, we have the display server itself, we have a compositor, and the window manager usually in one process. And with Wayland, we take those three responsibilities and combine into one display server. And it's a display server, it's not a rendering server, where X today lets you send rendering requests to the X server, which the X server will then execute and render for you. The Wayland doesn't have any rendering API, so you can't use Wayland to render your UI. You have to render it locally using GL or software or some kind of local rendering API. And what Wayland lets you do is take that buffer, the result of your rendering, you take that buffer, you pass it to the compositor, and then that buffer gets integrated into the complete desktop image. So writing a complete new display server sounds ambitious, and it sounds, well, it's something that a lot of people have tried in the past, and a lot of efforts didn't end well. And it turns out that at this point in time, where we are with X, with our kernel infrastructure, with our 3D drivers, it's not a crazy project anymore. It's more or less a refactoring and cleaning up what we already have. So we're consolidating what we're doing today. We're refactoring the display server to support the UIs we actually use today. So just to recap, fast, but what X did in the past, how we used X in the past, and how our UIs worked in the past. We used to have a lot of, and there still is a lot of functionality in X that does all the rendering. So when you render rectangles, lines, white curves, and so on, the X server has code to rasterize all that rendering. It has code to manage the state, how thick do you want to have your lines, and what's your stipple, and so on. And all this graphics state is managed by the X server. There is API and protocol to change that state. And we have a lot of code to accelerate all that rendering. But today we don't use any of that because applications render themselves. So we have a really big protocol because rendering APIs are complex. They have a lot of state, and we have all that protocol in the X server to render, and we don't use it because it's all happening locally, and we only share the buffer at the end. Another thing about the X server is that it has a fairly complex Windows system where the way Windows work are a recursive tree. You have the root window is the top window, then you have sub windows so that you can move around, and those windows can have sub windows, and it goes all the way down. You can nest it as deeply as you want it. And in the past, toolkits used to use this functionality to say, here's my input field in my window, and you could have the X server manage that input field. You could set a different background color for that window, and the X server would repaint part of that. It would change the cursor for you, and it would do a lot of halfway of the rendering. And the idea was that if you're on a slow connection, that window gets exposed and you have to repaint it. The X server can kind of repaint it halfway there, and then you can repaint the cursor and the focus in there. And if you move across the window, you don't have to round trip to the X server to get that cursor right. So that's what the sub windows did for us in the past, but none of the toolkits use that today. Instead of using a sub window for an input field, they just draw a rectangle there. Instead of changing the cursor by setting a different cursor for that window, they watch cursor motion, and when the cursor moves into that field, they set the cursor. So a lot of the toolkit has moved away from this model, and they just have one big window, and they manage all this structure within that window themselves. So a lot of the complexity we have in X to do that sits unused, and input delivery and exposures and all that stuff is really complex, and nobody knows how it works very well. Well, a few people do, and that's part of the problem, is that we have a lot of complexity nobody uses. We have to keep it running, and there aren't a lot of people that really touch that stuff or know how to change it without breaking the world. So another thing that changed is that a lot of the driver side of X has moved into separate reusable components or drivers in the kernel. Not long ago, an X driver would have to set the mode, program the registers to bring up the display in the right mode. It would have to share the hardware with GL clients by using a big lock and programming the registers. And it was very hard to have a system where you could have several clients and they're using the same hardware. And again, the acceleration code that we use for accelerating X was also tied up in the X driver. So it wasn't really possible to change the way things worked. It was always tied up in this X model. And so what changed there was we moved out mode setting into the kernel. We moved out memory management and execution management so that when you submit rendering commands to the hardware, the kernel knows how to multiplex and arbitrate between several clients trying to use the hardware. And we made the GL drivers independent of X so that we could use them as EGL drivers or GLES2 drivers, and we made it possible to use those drivers directly on kernel mode setting without X. So a lot of the infrastructure that was tied up into this big monolithic X server has been split out into reusable components. And it even for the input side where we get input events from mouse and keyboard has been changed. It used to be that the X server had a lot of code to go out and parse serial protocols from different mice. It used to be able to talk to different keyboards, and it was a mess too. We had 10 different input drivers for different space balls and so on, whatever the different input types work. But today, all we do is talk to the EVDev driver. The EVDev driver is a kernel interface that lets us talk to a wide range of different input devices with a uniform interface. So whether you plug in a plain old mouse, or you plug in some kind of weird 3D controller or a touch screen or a keyboard, it all shows up as an EVDev device with a uniform interface. So the whole input driver story is simplified to, you don't need to understand serial protocol or configure the baud rate on your mouse. It just works today. So, and those were all infrastructure changes that made the stack more modular and reusable. But the biggest change that happened in the past few years is that we started using compositors, and we went from a Windows system that would render on demand to something that where clients render into back buffers, and we have this compositor process that combines the Windows surfaces into the desktop image. So the idea is that with X, we had this big buffer, the color buffer that actually is what you see on your screen. And when clients want to render into that buffer, they send commands to the server, and the server will clip those commands against the rectangles. So if you're overlapped by a different window, we don't get to paint in that area. So we share that big buffer by going through the X server, and it's clipping rectangles. But with compositing, we went to a model where each application now has its own back buffer. So you can, if you're a little window up here, you have your own back buffer, you render into that, and over here there may be a web browser rendering into its own window, and maybe you have a terminal here rendering to its own window. So every application has its own back buffer. The compositor will take these individual buffers and overlay these different buffers into the screen, and that's how the screen gets painted in a composited desktop. And it used to be that people with composited desktops were all about wobbly windows, spinning cubes, and windows on fire. But today we've gotten to a point where it's not so much about the effects anymore. It's about the better quality you get from the desktop. You don't get flickering when you move windows around. When a window shows up, it doesn't show up blank and then get repainted almost immediately. But you still see that flash. When you resize window, you don't see the window bars move, the window frame move, and then the window repaint. So a lot of that flicker we had in the old desktop went away when we started doing compositing, because the compositor can batch up all this rendering and make sure that we don't clear in one frame and then repaint in the next, but clear and repaint and only then show the result. So today compositing is a requirement for a good desktop experience. It avoids all the flickering and bad experience with the old model. So with Wayland, one thing that happened was that when you look at the X model as we have it today without Wayland, we're running the compositor, which is responsible for painting the entire desktop. It has these textures coming in from clients that are the window contents. It knows how these textures are layered, and it knows how to render that entire stack and present the complete desktop. The applications do their rendering locally and don't talk to the X server when they render. They just pass the buffer to the X server, and the X server passes that buffer to the compositor. And similar, when the input comes into the X server, it gives it to the client, and the client update the window accordingly, and then re-render, pass it back to the server. So what happens here is that the X server doesn't do much anymore. It takes the input, gives it to the client, which is actually not the right model, because since the X server technically doesn't know where the windows are on the screen, the X server can't decide who should get that event. So the only thing that the X server really does today is actually broken. And everything else is something where we could, instead of having X in the middle, we could hook up the application directly to the compositor. And that's what Wayland does. We make the compositor the display server. And the Wayland protocol is essentially a communication channel between the compositor and the clients that lets the compositor send
input events to the clients, and the clients will then update their buffers and send the new buffer back to Wayland. So it's a much smaller protocol. It's a much simpler model than X. We don't have a rendering API. We don't have font rendering. We don't have font management. We don't have all the sub windows that you used to have to help rendering. It's a tiny protocol, and it works because we're not really using much of X anymore. Yes, so that's what I just said. The state today is that we split out all the hard parts of X, and the X server is essentially just a mediator or a middleman between apps and the compositor. And the only point where we still use X for something is the input, which should go through the compositor as well. So that's the setup. That's what makes Wayland possible. But how is it feasible? How can we actually pull this off? And again, the thing is, the way we split out all the functionality of the X server makes it reusable in different ways. So the kernel mode setting that lets us configure the output and do page flipping and set up overlay planes is available for general use. So we can use, the compositor can use this mode setting library to control the screens, multi-head, and page flipping. And we can load the DRI driver. The same drivers that we use under X for 3D are available as EGL drivers now. So we can load those drivers. We can configure them to render to the frame buffer, to the kernel mode setting frame buffer that we're using. And then what we have at that point is we have accelerated GLES2 on the Linux frame buffer. So that basically takes care of all the hardware, and we read input from EVDev devices. So that covers all the hardware interaction that a display server needs to do. We have APIs for this, and then not just APIs, but APIs that we're also using for X. So we're using the same drivers, the driver community, the driver developers that works in Mesa and EVDev. They can enhance and improve the stack as they go, and it benefits both Wayland and X. And we're not splitting. We're not saying you have to write Wayland-specific input drivers. And at the same time, a Wayland compositor doesn't have to have hardware-specific code paths. We don't do something different for this chipset and then something else for that chipset. It's all EGL. We talk to EGL, which is cross-platform and cross-chipset API for doing 3D rendering, and we're able to actually write a display server that doesn't have any hardware specifics. It doesn't have to load drivers. It just uses GLES2. So what kind of compositors would we be using, or do we use with Wayland? And there are basically two approaches here. You can write one from scratch. That's just a Wayland compositor and nothing else. And that's actually what I'm using here. The presentation and everything here is running under the reference Wayland compositor. This is the Western compositor, and it is a really small project. It's 10,000 lines of code, and it does mode setting. It does handle the events. It has a. We can have a look here. So here's the presentation application, and it runs. It runs the application. Here's a GNOME system monitor. This is GNOME terminal, and there is a calculator. So it's 10,000 lines of code that lets you run a compositing display server window manager, and it is quite usable. But at the same time, it's not a full-featured window manager as we know it from X. Doesn't handle all the key bindings. It doesn't integrate with apps in the same way, and it is in many ways It is a reference implementation, but it's also useful on its own. Depending on what you're trying to build, Western is a good choice for your system. If you're building a mobile device where you don't have a lot of legacy X application you want to pull in, you could base it on Western. You could say, here's Western, these are the toolkits, and you could build your own desktop or mobile UX or user interface on top of that. But for the existing X desktop environments, a more likely path is probably to take the compositor that those environments use and then enhance them to also be Wayland compositors. So for example, for GNOME 3, which uses the Metacity and Clutter-based compositor, we could add compositing functionality to that one. And then we can run a mix of X and Wayland clients, and over time we can phase out the X clients and eventually get to a point where we run native Wayland clients. And we have a talk about this in the X developer room. That's the X developer room in building. I forget what building it's in, but upstairs. Oh yeah, it is K. Yeah, and so Robert Bragg is going to talk about his work on Modder there, and he's got a fancy demo of Modder that he'll show off. And I forgot to mention that there's also a talk about how KMS and the new KMS sprite feature is going to work with Western, and Jesse Barnes is going to talk about that. So this actually ties into a good point, that since the compositor now is in charge of mode setting and controlling the overlays and planes that happen, we don't need a lot of complex protocol to tell the compositor that I want to use an overlay plane, I want to use this. The compositor is, on one hand, has all the surfaces that we need to show on the screen for any given frame. The compositor has all those surfaces in a big data structure and can look through that data structure and see this surface is suitable for a hardware cursor, or this surface is a YUV surface that we can use a hardware overlay plane to display. So the compositor is in a position where it has, on one hand, all information about all surfaces on the screen, and at the same time, it knows what hardware it's running on and can use that hardware, scan out hardware to accelerate display of this surface stack. So if you want to use a hardware overlay to display a YUV surface, or even an ARGB overlay to accelerate the rendering of the current active application, that's all possible. So there's a lot of more possibilities for optimization when you have both the surface stack you want to display and the hardware that's going to display it in the same process, and you can look through it and start optimizing. So the other side of Wayland is the client side. And when we switch display servers, the one question is, what do we do with the drivers and the servers? How do we move those over to the new system? The other side of the question is, what do we do with the clients that we have now? Because we have a lot of clients on the X. We have desktop environments. We have toolkits. We have a lot of functionality that we just can't throw away. We have to have some kind of migration path where we can pull it over without too much effort. And it turns out that most applications and most UI, most desktop environments we have all use toolkits. Nobody today talks directly to the X server. If you want to draw a window with buttons and scroll bars, you go to Qt, you go to GTK, you go to EFL, you go to one of the toolkits out there that makes it easy, and you put the scroll bar and the buttons where you want them, and most of the time you don't even know you're running on the X. So it turns out that we can get really far towards getting the client side of our graphics architecture running on Wayland by just pulling the toolkits. And we have started this effort already. We worked on GTK 3, we worked on Qt, and we didn't work on EFL. Karsten and his minions started working on that, and they made a lot of progress already. And are you done?
Shared memory buffers work, but they're not as well as they should. EGL and GLES clients done work, but there's some interesting bizarre bugs in Western that they come out. We'll have to talk about that later.
All right.
Like, Western literally will lose update regions and have like leave garbage on the screen and stuff. There's
Right.
weird stuff there. And that's all done. Input is done. We have client-side decorations done. And Enlightenment Compositor also does compositing. Now at Wayland, it's halfway there. Shared memory clients work. The GL stuff is now beginning to work, but it's...
Yeah. So Enlightenment is a long way there as a Wayland compositor. EFL is there. GLES2 works. Shared memory still has work to be done. But a lot of progress is made there, and it hasn't been more than a few months since you really started working on it. 2 months, and again, because a lot of the infrastructure is already moved client side, we're not changing the way we render fonts. We're still using FreeType or font config. We're not changing the way we use OpenGL. So it's a lot of the porting effort isn't too hard. GTK3 is something that I've been working on myself, and it's a big old toolkit, so there's a little more effort in moving it along. But fortunately, a lot of the community people that work on GTK or the Red Hat guys have done a lot of work where the dependence on sub windows that I talked about before is removed. The use of the X rendering API has gone, so they all use Cairo now. So GTK works very well on Wayland as well. And I think the Clodder port is mostly complete. Clodder is a very small toolkit, so that's something that can be done without too much effort as well. And there are a few common challenges or themes that come up when you look at porting a toolkit from X to Wayland. And porting away from X rendering is something that most toolkits have done. There's not a lot of toolkits out there that use X directly now. They all have some kind of internal abstraction that lets you render to a different API, or maybe they're using GLES2 or regular GL, or maybe they're using Cairo. So a lot of the X dependency in the rendering pipeline is gone, and we don't have to make any changes there. A bigger challenge is the client-side decorations, where X today have a window manager that draws the decorations around the window. We, in Wayland, expect that the client itself will provide a decorated window. So that's a challenge for some toolkits that they don't expect this kind of redirection or extra borders to show up, but it's something that can be worked around or fixed in one way or another. Another big challenge is that Wayland doesn't have grabs. And grabs is this feature in X where you can say, I want all the keyboard events and all the mouse events right now, and then nobody else gets those events. If that client then falls asleep or something, it basically leaves your display server stuck, and nobody else can. You can click in other windows, you can't use the keyboard, and you're basically stuck. So Wayland doesn't have that feature, and it turns out that we don't use that feature very often anymore. And when we do, we can change the display server to help out. The only example that I've come across in porting various toolkits is pop-up menus. When you click to pop up a menu, you get a drop-down menu, and at that point, most toolkits will grab the X server because they don't want you. If you click outside that menu in somebody else's window, they want to pop down that window and make the menu go away. And that's one of the few places where toolkits still use grabs today. And the solution that we've come up with is that we can just tell the compositor that this window is a pop-up window. So please change the input delivery path to work like that while that window is visible. And when that window goes away, either by clicking outside or if the application closes it, we're back to normal. So there's no way you can get stuck with a grab where all input goes to one app that's not responding. But it does mean that we have to look through the toolkits and make sure that when they pop up a pop-up window, they do it with the right way and get the input processing right. And another big difference that's challenging in some cases is Wayland never tells you where on the screen your window is. And this sounds weird, but it's one of those things that in X prevent us from ever doing input redirection correctly. So when the compositor rotates or scales down a window and puts it over here, the X server can't cope with that because we use in X compositors, we still rely on X for delivering input events. But when the window is rotated and off to the side, so the X server cannot represent that transformation. It cannot take that into account when it looks for the window to receive the event. So we fix that in Wayland by having the compositor receive the event from the hardware, and then because the compositor knows how it transformed or moved the surface around, the compositor also has to know how to find that surface and tell the client what is the location of that click within your surface. So that's all good, but the problem is that once we go to that model, we can't just tell the client this is where you are on the screen because we can't communicate that transformation. It could be that the window was bent or put around a sphere or something, so it could be anything that we can think of. So we cannot communicate that to the client, so the client can't know where it is on the screen. And that it works mostly, but some of the things we run into is that some clients want to know where they are on the screen when they pop up their menus, so that the menu doesn't go out over the screen edge. And so there are a few corner cases where the assumption that you know where you're on the screen breaks placement or other geometry problems.
What about porting things like wine? Because that's when you're porting a display system. Even X on Wayland will require that it emulates these features across all those clients.
Yeah. What happens when we want to put X on or wine on top of Wayland, where a client in the X server expects that it can look at the screen geometry and see where it is and then place the windows accordingly. So one thing is we can let the X server know where the windows are, and that will break pop-up menus in some ways because we can't pop up windows correctly if the application really is rotated up in the corner. We can't tell the X server that, and then when the X server pops up the window, it's going to break. The other things is that we can just not tell the X server about it, which means that it's going to break in some other cases. So there are some integration issues where we may or may not be able to get the exact same behavior as you expect from wine or from X. And the question is, can we live with that, or do we have to work around them, do some more work to work around? I think we'll try for living with it and then see if it really is a big issue. But we have the option of extending the protocol, but it does really break the idea in a major way if you start telling applications this is where you are, this is how you transform, because you can't give clients that assumptions. You can't have clients knowing where they are because they can't know. So the last point here is that aside from porting the toolkit, which will take care of a lot of apps, there are still apps out there that go around the toolkit and get some X-specific API. Maybe you want to talk to X render, you want to talk to, maybe you want to set a window property on the root window, or you want to do something X-specific. A lot of apps do that. And what happens is when you run an app like that, it assumes that it's running under X, and it will cast some some object in the toolkit to an X-specific object, and that'll then crash. So the solution there's no silver bullet here. We have to go through the apps and say, this apps will unconditionally cast some object to an X-specific object, and you can't do that, and we have to work around that on a per app basis. So there is some work to do there, and it depends on how well your toolkit isolates you from the Windows systems. Some toolkits are pretty good about this. Qt, for example, goes a lot longer in this respect because Qt has a longer tradition on running on different operating systems, different Windows systems. And I think GTK, for example, has a lot more cases where apps will go and access the X server or X specific behavior. But it is just something that we have to. I mean, it hasn't been a problem before because we're always running on X, but now there is some work to do in tracking down those accesses. So I guess I kind of touched upon this before, but the driver support side is basically if you can run DRI2 with an open source driver on your X server, you can run Wayland today. And what we've done is we've added a few extensions to Mesa. All the infrastructure for supporting EDL on KMS and Wayland is all part of Mesa. It's part of the general infrastructure. So when somebody sits down and adds support for a new chipset or a new complete driver to Mesa, chances are that it will just work with Wayland because it's part of the Wayland support is part of the general infrastructure. So adding a new driver into that framework automatically gives you Wayland support. And similar with if you go and you add kernel mode setting support to your driver, that's going to work with the general purpose kernel mode setting API. So when Wayland tries to do mode setting on your new chipset, if that's supported with kernel mode setting, it's going to work with Wayland. So the requirements from Wayland are very similar to an X server with DRI2. And as I said, Mesa and the Linux kernel gives you all this out of the box for the three big chipsets out there. And people always ask what about the binary drivers from other vendors? And I don't know, and I can't speak for them. So I don't know what plans are there. But the one point about this is that we're not dependent on Mesa specifically. We're not dependent on KMS specifically either. You can write a compositor that uses a different mode setting API, a compositor uses a different EGL stack, and you can get to the same point where we are today. You can run the compositor on that hardware without too many changes. So one of the things is that we've been working on Wayland for quite a while, and for a long time it's been a research project. We've been breaking protocol, we've been rewriting this and that, and we've been refactoring, taking something, moving things around between different processes and trying to figure out how things should work. But we're getting to a point now where we haven't really changed the protocol in fundamental ways for a long time. We had the same API, the same architecture, the same model for how things work for a long time now, and we've come a long way with porting toolkits. We have Clutter, EFL, TTK, Qt. They're all running on Wayland. There are loose ends, there are things to finish, but they're so far along that we're pretty confident now that the model we have, the protocol we have, is something that we can push towards the 1.0 release pretty soon. Yeah. So the idea is that once we get to 1.0, we don't expect that it's not world domination. We don't expect that every desktop out there will run on 1.0. What we do expect and what we want to signal with the 1.0 release is that from this point on, we're not going to change the protocol in a way that breaks your toolkit. We're not going to change the API in a way that breaks your toolkit. And we've done this in the past. We've had to move things around in the protocol. We had to drop interfaces. We had to break interfaces. And we played around a lot. But we're getting ready to say that we can do a 1.0 and we can release something that we will only increment. We'll only add functions. We'll only add new interfaces, but we won't break anything anymore. So we're getting ready to commit to the interface. To get there, we have a couple of releases that we're talking about. We're going to do a 0.85 release soon, today perhaps. And the plan there is that this is a snapshot of what we have now. It's not something that we commit to. We're not going to freeze the protocol now. We know that we have changes we need to make, but we know what they are, and we're confident that we can make them within the next half year. And once we get to that point, we start doing the 0.90 releases, where we call it the beta releases, and from there on, we really don't expect to change the protocol, but we're not going to rule it out. It could happen, but it's still beta. But we expect that from there on, we can keep the protocol and API frozen, and then eventually we'll do the 1.0 release somewhere in 2012, 13. Yeah. I don't know. I mean, we have work to do between now and 1.0, and it's not trivial. And there is things that we need to move around. But I do expect we can at least get to beta release within 2012. And if we end up going into 2013 for the 1.0, it won't be far into 2013. Yeah, so this is just what I just said, I guess, elaborating the snapshot. The thing is, Wayland, as it is now, is actually used in different projects that, and I only know of a few of them. I think it's out there being used by a lot of people. So what we're doing with 0.85 is we're making a snapshot now, because this is useful as it is. We're going to move things around and we're going to break things, but let's make a stable branch for what we have now, and we can maintain that in the fixed box and keep that alive. But at the same time, we are going to break the API and the protocol. But we're making a snapshot because it is in use, and it makes sense to keep the current protocol stable and have a stable release branch for that. So that's the idea with 0.85. 0.9 are the beta releases, and then at 1.0 we commit to the protocol and say this is done. Okay, so a quick recap of the talks that we have going on. We have in the XOP dev room, here's the room number, K3401. We have Rob's talk about writing a Wayland compositor, where he's going to show off some of the modder work he's done. We have Jesse's talk about plane support and how we can use this new sprite feature we have in some of the new Intel chips that lets you put a surface in its own sprite, and then we can move that around without re-rendering the entire thing. And then I have a Q&A session with Robert Bradford, where we talk about some of the things we came across while porting GTK, and we'll be a Q&A for toolkit developers that are interested in supporting Wayland. And questions? Yeah. Yeah.
Well, you talked about grabbing windows, and I'm wondering, usually games also grab windows, right?
Yeah.
What do you expect from that? What do you expect to handle?
Right. So games often grab windows, and what do we do for games? And the thing about games is they often grab the window because they want relative pointer motion. When you're running around in Quake and you're running around the corner, you don't want your mouse to scroll out the window and stop sending events. You want to keep receiving those relative events. And what games often do there on the X is that they grab the pointer, they move out the window. If you get too far out of the window and you might hit a screen edge, they warp the pointer back in. So it's really a hack to keep receiving those mouse events so that you don't end up hitting a screen edge where you wanted to turn around in your first-person shooter. So for that, we're going to go the same direction as X input are going, where we can provide relative input events. It may or may not be part of the 1.0 release, but we do expect that it's something we can add on later without breaking anything. And it is a feature we want to do, but it's not something we want in 1.0. But it is on the roadmap. We're aware of that use case. Thanks. Carsten?
Same vein with the grabs, screensavers.
Yes, screensavers, screen locking. That's also something we talk about, and whether we do it as 1.0 or later is not decided. But
It's intended as an extension, protocol extension.
it will be a protocol extension, yes. And it's also something, if you build your own UI, EFL-based UI on top of Wayland, you can write your own compositor, you write your own toolkit, and you can put your own extension in that compositor, and you can have your own screensaver as part of your complete UI that talks to the compositor. So we don't need to standardize every single thing we have on X today. If you're tailoring your compositor and your core UI together, you can add extensions to tie the components together. Up here. Right. How does having a separate buffer per application affect the memory footprint? And that's really an inherent property of going to a composited environment because every application has its own background buffer now. But it's not a decision that Wayland makes. We don't force this on you. If you're using GNOME 3 or KWin or Compiz, that's already the case. We already have a separate buffer per window today. So we're just taking that model and making it the default model. And with Wayland, we do have the option of actually throwing away the back buffer. If we have a window that's not visible on screen, we can free that buffer and we can ask the client to render it when we make it visible again. So we do have a little more flexibility in optimizing the memory uses here. For example, if you're on a UI where you have exclusively full screen applications, you can say when you switch from one app to the other, every other app is no longer visible. And you can ask those apps to throw away their backing buffers. So if you're on a memory constrained mobile device, you actually have more flexibility in controlling buffer uses than you have with X. Yeah. Remote desktop, remote display. This is something that always comes up in the forums. When I read comments about Wayland, there's always two things that ends up in framework. There's client-side decorations and there's remote desktop. And the remote rendering feature of X is based on sending these rendering commands across the wire, and then you can have a client on this machine showing on that machine. And we can do that with Wayland too. It's going to be different then. It's not going to be rendering commands you send across. We're going to send bitmaps and bitmap updates across. And a lot of people think that this is horribly inefficient, but today you often can't render your UI without shifting a lot of images across the wire anyway. And it's also inefficient in that if you do remote rendering, you often end up with a lot of round trips to query the state of your rendering, of your remote rendering API before you can even render. But with Wayland, you do all the rendering locally, and once you're done, you just push the result across the pipe as a compressed partial update of your window. So it can be done really efficient, and we can do it with native Wayland clients, and it's going to be amazing. But we just don't have it as a priority right now. There's nothing in the architecture that makes it impossible or even inefficient. It's just not but the thing about it not being a priority is something that people always latch onto, that if we somehow don't design it into the Windows system as a core feature, we're never going to get it right. But we are going to get it right. It's just not a priority. Okay. Yeah, so that's another question where people, from X, we're used to being able to customize your X desktop by using different window managers. Some people like Fluxbox, Awesome, some people like GNOME 3, and there's always been a tradition of choice here where you can have the exact desktop you want. And that's a good question because with Wayland, there's the barrier to entry is a little higher because you can't just write a window manager, you have to write the entire Windows system now. But again, the Western compositor I'm running here is 10,000 lines of code, which is, there's a lot of smaller Windows managers out there that are smaller, but it is possible to say we're going to write our own Windows system, our own Wayland server, and make that behave as a tiling window manager or something. Okay, the other option for there is that you can also make, Western has a plugin API, you can write your own plugin to Western to implement the window manager behavior you like. So that was the last question, and I guess we're done here. Thank you.